While watching this class, you will regularly need to pause the video to complete exercises. There are two platforms where you can complete those exercises. One, on the Accelerated Computing Hub. Two, on the DLI platform. For more information, please check out the intro section of the first video. All links can be found in the description below. Okay, so hi everyone. So in the previous section, we explored how a synchronous parallel algorithm can further enhance performance. But what if there's no parallel algorithm for your specific use case? So I can't use any CUDA libraries, I can't use Trust, I can't even use any fancy iterator because what I want to do is very specific. That's when you actually need to write your own algorithm using CUDA kernel, and that's the goal of this section. So first, we'll talk about what are CUDA kernels. We'll learn about atomic operation. We'll learn about the notion of synchronization between threads. Then we'll talk about shared memory and how it can improve performance. And finally, we'll discuss about what we call cooperative algorithms. So remember, usually the CPU calls a host function while the GPU calls a device function. And so invoking GPU work from the CPU requires a special mechanism. So far, we didn't really have to care about it. We just called thrust, and thrust would do the work for us. But now, because we want to implement our own algorithm without relying on any library, not even thrust, we need to understand how to launch code on the GPU ourselves. So let's do a quick recap on execution space. So far we have discussed about host functions. So that's when you add host onto a function to say that this specific function will be executed on the host. And so the compiler has to create CPU instruction for this function. We also talked about the specifier device, where this time when you put it on a function, it tells the compiler that it should generate GPU instruction for this function, allowing it to be executed on the GPU. And so there is another one that we haven't discussed yet, which is called global. And so global will allow, just like device, the compiler to generate GPU instruction so that the function can be called in the GPU. But this time, because the function is tagged with global, this function will be called from the CPU. So the CPU will make the function call to this function, but the function will be executed on the GPU. And so that's what we call a CUDA kernel. So calling a CUDA kernel from the CPU looks unusual because of the triple angle brackets with thumb number inside. So what we can see here in the top right. So let's discuss about what those numbers mean. We'll discuss those what those numbers mean later in the course. And another important detail when you launch a kernel is it's just like CUP. It's synchronous. So the CPU will launch the kernel. So the kernel will be launched on the GPU, but then the CPU just continues. It doesn't wait for the kernel to come back from the GPU. Not like thrust. So it's really like CUP. It's asynchronous. So before we start writing our own CUDA kernel, let's recap how our simulator currently works. So if you remember, we use an empty span to have a 2D view of the temperature grid. And then we transform cell indices into new temperature using cub device transform. Under the hood, cub implements device transform using CUDA kernels, which is why they run asynchronously. So let's see how CUDA kernels actually work. So it's best to start with the code that you're already familiar with. So let's try rewriting our own simulator and launch a kernel directly rather than relying on thrust to do that. So on the slide, you'll see a simple CUDA kernel example that iterates over all the cells and transforms their indices into new temperature. So notice when we launch the kernel, we use the triple chevron syntax. And there is a force parameter, which is the CUDA stream. And so by passing a stream here, you can run the computation asynchronously on a specified stream, just like what we did when using CUP. But so as you already know, the GPU doesn't automatically and magically parallelize your code. This means that a single GPU thread is computing each cell in serial in this example. So overall, this makes our kernel roughly 10,000 times slower than CUDA, because here, the only thing we're doing here is launching a CUDA kernel, but with a single thread, and this single thread is doing the whole computation. And so obviously this is way slower than using all the threads of the GPU. We can easily increase the number of threads that a kernel uses. So for instance, to launch 2 threads instead of 1, we just pass 2 in the second parameter. So in this triple chevron syntax, the second parameter represents the amount of threads you want to launch. So you could just launch 2 threads. So you can see on the right that doing so using 2 threads instead of 1 almost doubles the kernel speed, which makes sense because we are using two times more threads. But simply launching more threads isn't enough. If they are all processing the same cell, there are actually no speedups. So to fix this, we need to modify the kernel so that each thread can distinguish itself and handle a different subset of cells. We can't have both threads doing the same thing, right? The first thread needs to do some part of the array, and the other threads need to do another part of the array. So that's where what we call thread idx.x comes in. So thread idx.x is a built-in variable which is available when you're inside a CUDA kernel, and it holds the index of the current thread. So if we launch 2 threads, thread idx will be equal to 0 in the first thread and in 1 in the second thread. And so with this approach, if each thread process is going to process a different subset of cells. And so in the kernel, we first read thread idx to identify what's the current thread index. Then each thread starts by processing the cell whose index matches its own thread index. That means that the first thread will work on cell 0, and the second thread will work on cell 1. And so after finishing one cell, we move ahead by adding the total number of threads of the cell index. This way, the first thread takes cell 2 next, while the second thread moves to cell 3, and so on. So during the very first iteration, thread 0 and 1 are processing those 2, and then those 2, and so on. So notice how these schemes allow us to compute all the cells in parallel, such that one cell is never processed by multiple threads. Like one thread is always just handling one cell, and one cell is always handled by just one thread. And so another observation that we can do is that there's nothing specific in our code that would limit it to only 2 threads. So we could use more than just 2 threads. So let's try increasing the number of threads working on this CUDA kernel. So here, if we go from 2 to all the way up to 256 threads, it goes obviously even faster. So our performance have improved significantly because we're using more threads, but as you can see, we're still very, very far from what CUDA is able to achieve. So why not just add even more threads? So if we tried launching the kernel with, let's say, 2048 threads, then suddenly you get this cryptic error, which will say invalid configure argument. And so there's something here that we're not understanding because we think we should be able to launch as many threads as we want, but actually we cannot do that. So it turns out there is a limit on the number of threads in a single thread block. So what exactly is a thread block, and why does it matter for our kernel launch? So in CUDA, threads are grouped into what we call thread blocks. And the entire collection of all the thread blocks is what we call a grid. And so each thread block can contain 32, 64, 128, all the way up to 1024 threads, not more than that. And so when you're launching a CUDA kernel, all the thread blocks will have the exact same amount of threads. And when you're using thread idx.x, what you're getting is your thread index inside this local block. So if your thread 0 in block 0, you will get 0. And if your thread 0 in block 1, you will also get your thread idx.x equal to 0, because this will return the index inside your block and not across blocks. So here, for example, on the screen, you can see we have 3 blocks. So here in block 0, thread 0 and thread 1 do get 0 and 1. Same here, thread 0 and thread 1 do get 0 and 1. And same for block 2, because again, those indices are local to the thread block. You can also fetch the width of your block by using block dim_x, which is here equal to 2, because we have 2 threads per block. And you can also fetch the length of the grid, which is here griddim.x, which is equal here to 3, because we have 3 thread block. And finally, you can also fetch what's your current block ID. So here we are in the first block, so block idx.x is equal to 0. Here in the second block, block idx.x equal to 1. And here in the third block, block idx.x equal to 2. And so it's by combining all those information that we will be able to compute what's our current location in the whole grid. So block dim_x will tell us how many threads we have in each block. And so here we have 2. While the grid is 3 because we have 3 blocks. So by multiplying block dim_x by grid dim_x, we can get the total number of threads in the grid. So here, for example, we have 3 blocks. We know that because we have this grid dim_x. And if we multiply that by the length of each block by using block dim_x, so 2. So if we multiply 2 by 3, we do get 6. And 6 is indeed the total amount of threads we have in the grid. So besides knowing the total number of threads, we also need to be able to know what is each thread unique index across the entire grid. And for that, we can use the block idx.x, which is what is holding the block ID. And so you can see that here, again, all the threads that are inside this first block, they will all have a block idx of 0. All the threads in this other block will all have the block idx of 1, etc. And so to calculate the thread global index, we multiply the block idx, so what's the index of my blocks, and we multiply that by the length of my block. And this way, we know what's the offset we have to take to arrive on the correct block. And once we are there, we just need to add what's my local thread ID. So here, thread ID x.x. So for example, the second thread of the last block, well, we use 2, which is our block ID x.x. So that's the index of my block. We multiply it by the length of one block, which is here 2. So this allows us to have an offset of 1, then 2, to arrive here in my current block. And then I can just add what's my thread ID x, which is here for the last thread, 1, and I get 5. And indeed, in the whole grid, this thread is the 5th thread. Here I have thread 0, thread 1, thread 2, thread 3, thread 4, and here thread 5. So again, by multiplying my block ID times the length of one block in grid dim, and then by adding the thread ID, I'm able to get what's my thread global ID in the entire grid. So now that we know how to find each thread unique index within the grid, we also know the total number of threads. There is one question that remains: is what kind of block size should I use? Because we just said I can launch thread blocks of size 32, 256, 1024. Which one should I take? So unfortunately, there is no magical number that is going to be the best for all the cases. So usually you have to fine tune this specific number, so the amount of threads per block based on the problem. But so one helpful guideline to pick for the block size is to always use a multiple of 32. So for example, taking 50 or 60 doesn't make a lot of sense. You should always use a multiple of 32. And usually a common default value that we advise is 256. But again, this is dependent on your problem, and you should look at which one is best. But if you really have no idea and you don't really want to care, you can just use 256. So the second question is how many blocks we should launch. So okay, my block is of size 256 threads. Now how many blocks, how many thread blocks should I launch? So the grid size will typically depend on the problem size because we want to maximize the parallelism. So the question is how to divide my element of my problem among the threads. So for example, if we want each thread to handle just exactly one element, if we just use a simple integer division, this won't work. Because imagine that we have 6 cells to process, and we choose a block size of 4 threads. If we do 6 by 4, so if we divide 6 by 4, we'll get just 1. So we will just use 1 thread block. But you can see that if we just use 1 thread blocks of 4 threads to handle 6 cells, and each thread is processing just 1 element, we're going to miss 1 thread block to handle the 2 last elements. That's why inside CUDA, we provide what we call CUDA seal div, which will round up to the integer above. So you can use this to automatically compute for you what should be the correct amount of thread blocks you need when you want to exactly have 1 thread per element. So in our example with the 6 and the 4, if you call seal div, that will return not 1, but 2. And so you will correctly, here in this example, have 2 thread blocks allocated with each one having 4 threads to handle all the 6 cells you need. And so to pass down to the kernel the amount of threads, thread block you want to use, it's the first parameter here. So you can first declare the block size. So here we took the usual 256. Then we want to know how many blocks I want. So to do that, again, I'm using CUDA seal div, passing my total problem size and the size of each block, which gives me the correct amount of total block I need. And then when I'm calling the kernel, I first pass what's the grid size, so the amount of blocks of thread blocks I need, and then the size of each block. So with these changes, we're now launching around 5 million threads, and we are now finally getting close to CUB performance. So of course, CUB still has a more advanced optimization under the hood, so probably you won't be able to match the speed of CUB. But for such a simple kernel, this is already very good to have achieved such a speed up by just adding more threads and correctly computing the IDs and the thread blocks. So we've modified our simulator, but haven't yet confirmed that it still works correctly. Because our setup is symmetric, temperature at the top and the bottom of the grid are identical. So we can do a quick smoke test by checking that symmetry. The idea is simple. For a given cell, we find its mirrored row by subtracting the row's index from the grid height. And so if everything is correct, the temperature of the symmetric cells should be nearly the same. So on the screen, you'll see a C++ function that performs this check. And so as part of this exercise, you'll have to turn this CPU C++ function into a CUDA kernel and launch it with the 777 syntax. And so by picking the correct amount of blocks, threads, etc. And so for this exercise, you'll have 5 minutes starting now. So to turn the symmetric check function into a CUDA kernel, we have to annotate it with the global specifier. So remember, global allows you to launch a code on the GPU. So this function will be compiled to be able to work on the GPU because we have specified global. But because we're using global in that device, this function is callable from the CPU in an asynchronous manner. And so after that, we need to launch it using the 777 syntax that we have discussed about. And so here, because there is no real parallel work, here we can just launch a single block with a single thread. And to make sure these checks run on the correct stream, we just specify as the last parameter the stream we want to use. Now, when we think about it, the entire row should be symmetrical, right? Not just a single cell. So in this exercise, you'll modify the kernel so that each thread handles exactly one column. And so again, for this exercise, you'll have 8 minutes starting now. So time's up. So just like before, if we use block and thread indices, we can compute what's the thread global ID. So that's what we do here in the top. Because we want to know which column we are, we use the block IDX, so our block index. we multiply it by the width of the block, and we add what's our current thread ID inside the block. And so by doing so, we can compute what's our column index. And so then when we want to call the actual kernel, just like before, we can declare the block width. So we took the default 256. To compute the grid size, we take what's the full size of the problem. Here in our case, it's the width. And we divide it by the block size using, again, this CUDA div. And when we call the kernel, we just pass here at the first parameter the grid parameter and then the block parameter. And so this way, each thread handles exactly one column and the entire row is checked now in parallel. But so by doing so, we have just caused our first out-of-bound access. Because we round up to make sure that each thread has at least one element, we might launch too many threads than the actual problem size. So in this case, remember, we are launching, in this example, we are launching 2 thread blocks, each with 4 threads, but we only have 6 elements in total. So while the first block will handle the first 4 elements with its 4 threads, the second block will also have 4 threads because all the blocks have the same amount of threads, but there are only 2 elements to handle. So the 2 last threads will try to access elements that are actually non-existent. So those 2 accesses by the 2 last thread of this last block will be out of bound. And so we need to find a way to fix that. And so one easy way to fix that is adding what we call a boundary check in the kernel. So right after we compute the global thread ID, we just need to compare this value to the total number of columns and skip it if there is no work to do. So here, after we have computed the global column ID, we just check is column inferior to the width, which we can find in the MD-span through extent 1. And so only if my column ID is inferior to this width, I'm going inside of here and doing the checks. But so how could we have discovered this on our own if we didn't know about those boundary checks? So at NVIDIA, we provide a special tool called Compute Sanitizer that helps to detect out-of-bound accesses and other memory issues in your CUDA kernel. So if you compile this simulator code with the flags shown on the slide, so what you can see here at the top, Compute Sanitizer will pinpoint exactly what line, on what line did the illegal access occur. So here, for example, you can see we really have all the information needed. We know he did an invalid global read, so it's not a write, it's a read, of what size? 4 bytes. That makes sense because we're using floats. We know it's coming from this specific kernel here, symmetry check kernel. We know the file, row symmetry that check.cu, and we even know the line 7. We know which thread in which block, and we even know what was the nearest valid allocation. And so here we know that this is actually coming from the last block where we did this out-of-bound access. And so this way, Compute Sanitizer is really giving us all the information we need to be able to understand that indeed what we were missing was a boundary check condition. And so actually MD-span can also detect out-of-bound access on its own. So by default, it's off, but if when you compile, you define CCCL enable assertion, just like what we showed on the top, this will make MD-span detect when you're doing an accession if you're doing an out-of-bound. And if you do so, it will trigger, just like you can see here, an assertion. So again, you will know which thread in which block made an out-of-bound access. So this works by just checking when we're accessing the array through the MD-span if what we're trying to access is greater than the size of the MD-span. So by adding those boundary checks, we've just fixed the bug. And so now it's natural to ask, so why do we need all this complexity of thread hierarchy with like the thread blocks, the grid, all of that? Well, to understand why all of this is needed, we first need to modify the problem a bit to see why the thread block hierarchy actually makes a lot of sense. So let's now create an histogram for the temperature that our simulator produces. So a histogram helps us see how frequently certain temperature range occurs. So let's quickly review how this works. So first, we divide the entire temperature range into different bins, and in our case, we will have 10 different degrees. And so for each cell in the simulation, we determine in which bin the temperature will fall into. And so a simple way to divide the temperature into the specific different bins is to round down. So for example, if a cell's temperature is 4 degrees, we divide by 10, and so we get 0. And so we know that this 4 degrees should go in bin 0. But if a cell temperature is, for example, 15, and so we want to put 15 in the first bin, well, again, you just divide 15 by 10, and this will give you 1. And so you know that this temperature 15 has to go in the first bin. So that's the example you see here. So we want to, in the first bin, we want all the things that fall between 0 and 10. So we just need to divide the input value, here the 2 or the 4 by 10, and those will give 0. So we'll go add that in bin 0. And on the other hand, here, all those 15 value that we want them to end up in this first bin, because it's between 10 and 20, we just divide this 15 by 10. This gives 1. And so we know we need to put that in bin number 1. And so once we have assigned each cell to the correct bin, we just count how many cells land in each of those. And so that count becomes the height of the bar we see in the histogram. And so in our example, we have 8 cells that fall in the first bin and 4 cells that fall into the second bin. And so this final visual makes it easy to spot patterns and see which temperature range are the most common in our simulation. So now let's think of building our own kernel signature to do this histogram. So because it's an histogram, it just needs one dimension. So we don't need an empty span, because empty span is a multi-dimensional span. And here we have just one dimension because we're 1D. That's why here, instead of using CUDA STD empty span, we just need CUDA STD span. And so in CUDA, just like in C++, span is a preferred way to access data over just using row pointers because it's safer, because as we have seen, it can detect out of bounds. You also avoid doing weird things with the pointer. You can also access the size and all of those. And so to construct a span, it's just like for the empty span, you just pass the data of the underlying container that you want to see as a span, and then the size, and that's it. And so then to access it, it's just like any regular container, like a vector, you just use the braces to access it. And so again, you can, just like for a vector, have access to the size of the element, and again, you're protected when you're accessing it. So with both the temperature and histogram passed to our kernel, again, we just need to compute what's our global thread ID using the same formula as always, with the block ID, the block dim, and the thread ID. And then each thread will load its corresponding temperature value and divide it by the bin width. So in our former example, it was 10, but here it might be different. And we do that to, again, find the correct bin index, in which we are going to add 1 based on our value of temperature. So in a production environment, you'd also want to ensure that this memory access is within bound. But so for simplicity in the slide, we'll skip the boundary check and just say that the problem size is indeed a multiply of the block size. So next, each thread reads the current count from its assigned bin and increment the value and write it back into the histogram. So here we first load what was the whole histogram value. We increment it. So let's say I found that my temperature is 4, and so I wanted to end up in the first bin. So I'm doing the computation with the division by the bin width. That will return to me 0, because 4 is between 0 and 10. So I'm getting bin 0. So then I'm going to fetch what was bin 0 value here by fetching in the histogram. Then I just want to increment by 1, because I have one new value that I want to add in this bin 0. And then I can just write back the result into memory, right? Well, if I do that, I don't see anything in my histogram. So it looks like something went wrong. So we have around 4 million cells in the grid. And so we like the bars should be in the million range. Well, and yet we don't see anything. So what happened here? The issue is that our kernel has a data race in the highlighted lines of the code here, the 3 lines. So all those millions of threads that are reading and writing the same memory locations everywhere. So let's see exactly what's happening here. So let's say we just have 2 threads, not 4 million, just 2. So we have thread 0 here. It want to read from bin 0, and the thread 2 also want to read from thread 0. So they all issue the same memory read requests. Okay. So thread 1 issues its memory read first in the histogram. Okay. And then the memory subsystem will respond with the current value stored in the histogram bin, which is here in our example 0. Then the old value that we have in thread 0 is updated to 0 because the histogram has just answered, well, in bin 0, I have the value 0. And so then thread 1 adds 1 to that variable and stores the results in new. But at the same time, while thread 0 is doing that, thread 2 is also issuing a read to histogram. But since this addition here has not yet taken place in memory, thread 2 is also reading value 0 from the histogram. And so 0 will also be brought back to the thread 2 old value. So then thread 2 adds also 1 to the old value and want to store it again. But at the same time, thread 1 is writing the value 1 to the histogram. So the 1 here gets written in histogram, and so now the histogram value is 1. But the issue is thread 2 also have the value 1, and it will also start writing 1 to the histogram value. So this thread doesn't have the information that this thread is currently writing the value 1, and so that this one should use this 1 value to update its own counter, but it's too late. The value was already read, and so it will also write 1 to this histogram. And so in the end, what the histogram will have inside here is 1, while 2 different threads were both trying to add 1 to this histogram value. So this is what happened with 2 threads. Now imagine what will be happening when millions of threads are trying to do that. That's why our histogram looks like it's empty, because when we are incrementing, we're not taking into consideration what the other threads are also trying to do, and this is what we call a data race. So to fix this race, we need to ensure that the read, modify, write sequence, this whole sequence, read, modify, write, is treated as a single indivisible memory operation. We don't want to have first the read, then the modify, then the write. We want the whole thing done in a single block. And so in C++, we can do that using atomic operation. And so you can think of an atomic operation as storing the instruction itself rather than just the byte. We really want to do the whole thing in just one go. And so in the example on the right, we store +1 into memory. And when the operation arrives on the memory system, it reads the current value, increments it, and then write it back the result in a single step. That you can see here on the left. Before we were first reading, then updating our local variable, and then writing. What we're doing now, because we're doing a fetch add, which is again what we can do in C++, all the operations are being done in a single one. And so by doing so, we're preventing any of the threads from reading or modifying at the same time. So each thread will issue a single atomic operation, while all 3, read, modify, write, will happen in a single sequence. And so we're lucky because CUDA also provides atomic through what we call CUDA std atomic ref, which lets you treat any existing memory location as an atomic variable. So you take any currently available memory location and you can view it as an atomic reference. So here we create an atomic reference to count 0 here in this example by just wrapping count 0 into an atomic ref. That means that then we can perform atomic operation on this count 0 by modifying it through the length of this ref, which is an atomic reference. So we can now do atomic add, atomic sub, atomic end, and every time we do that, those operations again will be atomic, so they will all be performed in a single operation. We won't have the first read and modify then write. And so this will allow us to modify count by multiple threads in parallel without having any race condition. So let's see how we can put that in our own kernel. So in our kernel, what will happen now is that thread 1 will use on the atomic ref a fetch add 1 to add 1 to the histogram, and thread 2 will also want to do a fetch add 1 on the histogram. So what will happen is now thread 1 fetches add, and this will arrive, do the read, do the modification, and do the write. All of that in just a single sequence, and the result will be stored back in memory. So now, when the thread 1 will want to do also its fetch add, when it will finally arrive in memory, here it will correctly read the new value, which is 1, because the fetch add cannot be executed before the first fetch add. So when this fetch add arrives, the first one is completely done. That's why we can correctly see the 1. We can then correctly increment by 1, and then correctly also update the final histogram value, which is now 2, back into memory. And so now we know that the result is correct and that no increment is lost in the process. And so what you will have to do in this exercise is to modify the current histogram code that we have to, instead of doing the read, modify, write in 3 lines, which creates a data race, now you have to use the atomic ref we just talked about to make the code work. And so for that, you will have 5 minutes. So time's up. So the modification is just a few lines, actually. All we need to do, just like when we showed in the example, is to wrap the histogram bin in which we want to write into an atomic ref. So now, when we write through this atomic ref, we're writing to histogram bin, but we're writing it through an atomic. So we're sure that when we're issuing something, here a fetch add, this fetch add operation is an atomic operation, and it's a single sequence doing all the read, modify, write, instead of doing it ourselves, which would create a data race. And so with this fix in place, our results are finally correct. So we can see an histogram that makes kind of sense. And so notice how the initial temperature are near 0, meaning that the first bin have the most cell in it. And so as heat spreads through the grid, we see more bins start to fill up. But so we have another issue now, which is that the performance is very bad. We're only reaching 6 gigabytes, which is very far from the maximum GPU memory bandwidth. So we really want to have something better than just 6 gigabytes. So last time we saw such poor performance was because of serialization, when we were just using a few threads instead of using all the threads. But this time, we don't have any loops in our code, right? We're using all the threads, we're using parallelism, we're using threads, thread blocks. So what is going on here? So this time, the serialization is coming from the atomic operation themselves. So while, yes, they solve the data race condition, because by design, they can't run in parallel because we don't want them to run in parallel, well, all the threads are targeting the same memory location. And so now we have many atomic operations which are getting queued one after another. So when we launch about 256 threads, we have about 16,000 blocks. In total, we're issuing 4 million atomic operations, and all of those are getting queued one after another. So this is obviously way too much. We don't want to queue that many atomic operations because that makes the code very slow. So what could be our options here to fix the problem? One solution is what we called privatization. So instead of having all the threads updating the same global histogram and thus having too many atomic operations being queued up on all the bits, we could allocate a small private histogram for each thread block. So each thread block will have a private histogram in which it can safely use atomics. And so this won't reduce the total amount of atomic operation we do, but now it's spread across more memory location. Instead of having all the threads writing in the same memory location, now first the thread blocks are writing in their own memory location before propagating them back to the global histogram. So when they're done, the block aggregates its count of its private histogram and update them to the main histogram, again, using one memory atomic operation. So in our simple two-block example, two block each increments their own local block histogram and only then propagate the result back to the full final histogram. So although here in this example, obviously it's not very helpful because we have just two blocks, imagine in the real case when we have 16,000 of them. So in this scenario, we'd have 16,000 private histogram updated in parallel, followed by just 16,000 atomic operation. So before we were doing 4 million atomic operation in global memory, which were all queued up. Now, because each thread block is just going to do one, we have just 16,000 atomic operation being done in global memory. So to implement this privatization, we need to add a new parameter to our kernel, which we call our block histograms. So next, we create a subspan for the current thread block portion of the privatized histogram. So the subspan function takes an offset and a size, and we just calculate the offset by multiplying the block index by the histogram size. So the first block has an offset of 0, the second block has an offset of 10, etc. And so this ensures that each block writes to its own slice of memory. So each block will have its own slice of this privatized histogram. And so then, just like before, each thread computes its bin index. However, we now increment the privatized block histogram instead of the global one, because we want to increment this privatized histogram per block and not the global one, because we just said like we want to reduce the amount of atomics we do in global memory. We want to do it in a privatized histogram so that we have less atomics being written back to this shared histogram by everyone. And so after that, each block adds its partial, have added to its privatized histogram, each block will add its private partial count back into the global histogram in parallel. So that's what we can see at the bottom. So in the code snippet, the first 10 threads in the block each handles one bin for the block private histogram and parallelizing the writes to the global histogram. So they use an atomic reference again to safely add their local count to the final histogram. But unfortunately, by doing so, we have introduced a new bug. So let's try to take a closer look at what's going on and why there is a bug here. So in the code, we have assumed that all threads finish updating the local block histogram before the next session of code begins. So we assume that all the threads write to the local block histogram before they write to the global block histogram. However, CUDA thread in a block, they run concurrently, and there is no guarantee of any ordering. This means that some threads in your spread block may not have even started, while others are already starting to exit your kernel. So you have no guarantee in which all of the threads in your thread block will be scheduled. So one could be at the very beginning of the code, while some may be at the very end of the code. So one of the possible scenarios is that some thread might have read the block histogram before it was completed by all the threads in the block, when after that they're writing it to the global histogram. So to fix this issue, we have to somehow make sure that all the threads are finished with updating the local block histogram before we read it. And for that, CUDA provides what we call thing thread. So thing thread is a special CUDA function that acts as a barrier for all the threads in a block. So when a thread reaches this barrier, it waits until all the other threads in the thread block also arrive at this barrier. So in that sense, it's similar to what we have in the standard C++ library called std barrier. But there's one important difference here. Every thread in the block must call think thread from the same logical path. So think thread will solve our functional problem, but there's still a performance concern. So if we look back at the libq++ overview, you'll notice two different sets of atomic reference. One in the CUDA std namespace and another in the CUDA namespace. So which naturally raises the question, what's the difference between the two? So CUDA std atomic ref and CUDA atomic ref provide essentially the same interface. However, CUDA atomic ref extends CUDA std atomic ref by adding a thread scope template parameter. So choosing the right thread scope can significantly impact performance. So let's try and understand better what thread scope is. So a thread scope represents the set of threads that can synchronize using a given atomic. So the scope could be the whole system, just the device, or even just a thread block. So for instance, when all threads are related to each other for an atomic, you would use CUDA thread scope system. This means that a thread from any GPU can synchronize with any other of threads in the GPU or even a CPU thread. It's the whole system. So CUDA std atomic ref is actually the same thing as CUDA atomic ref without the std, but that's the system scope. So the next scope, when it's not the whole system, it's the device. So device scope, it means any threads within a single GPU. So with this scope, multiple GPUs cannot issue atomic into the same memory location, nor can both CPU and GPU write in the same memory location. But any thread within the GPU can atomically write to a location, while any other thread from the same GPU is also writing to this same memory location. The final one, the final thread scope is what we call thread scope block, which restricts atomic operation to threads within a single block. So here, multiple threads, as long as they are inside the same thread block, can do atomic operation safely to the same memory location. But if a thread is coming from another thread block, this won't work. In our case, we can see that because each thread block is updating its own local histogram, this is perfect to use this thread scope block. And so this brings us to the next exercise. So this time, you'll have to use thread block synchronization to make sure that all the threads are done updating the block histogram before reading it and writing to the global histogram. And so if time permits, you can also improve the efficiency of the atomic operation by adding the thread scope to it. And so for this exercise, you'll have 8 minutes. The time's up, so let's see the solution. So first, we swap the CUDA std atomic ref to CUDA atomic ref. Then we limit the scope of atomic operation on the block histogram to CUDA thread scope block, because we know that when we're writing in this histogram, which is private to each block, we're only doing atomic operation by different threads in the same thread block. That's why we can use this CUDA thread scope block. Then we also added the think thread because after having done the fetch add, we want to make sure that all the threads are done updating this block histogram before updating the global histogram. And so when updating this global histogram in the same way, instead of using the default system atomic, we can use scope device because we know we're writing the histogram only from the device. But we have to use device and not block because here we know that this histogram is global and shared by all the threads in all the blocks. So we have to use scope device and not block. And by just doing those changes, we go from 6 gigabytes per second all the way up to 100 gigabytes per second, which is a huge improvement by just changing the scope of the atomic operation we do. But we can do even better. But so before optimizing our histogram kernel even further, let's revisit what we have learned so far. So we've just covered atomic operation, thread scopes, and spans. But what about our initial question? The initial question was, why do we even have thread hierarchy in the first place? Why do we need thread blocks? Well, let's take another look at thread block synchronization and thread block scope atomics, which are only available between threads at a given thread block. Synchronizing across a group of threads is much more expensive. So there is a benefit for thread hierarchy here. Synchronizing just the thread within a block is far less expensive than synchronizing all the threads within all the blocks. But are there any other facilities that are only accessible within a certain group of threads? Well, to find out, let's talk a bit about the GPU architecture. The GPUs are composed of uniform building blocks that we call SMs for streaming multiprocessor. This is what you can see here in green on the screen. And so a single GPU can contain hundreds of those SM. And so each SM has a lot of cores, but there is also a local L1 cache. Here we can see that each SM has its own L1 cache. And so the global memory, the main GPU memory, sits outside those SM. That's why it's called the global memory. So accessing global memory has a way greater latency than accessing something in the L1 cache because it's local to the SM. And it's also faster to access, obviously, the L2 cache than accessing the global memory. So because the GPU, as we have seen compared to CPUs, they usually do not have a great latency while having a very good bandwidth. That's why we want to make the latency as good as we can by leveraging the L2 and the L1 cache. So some feature like thread block synchronization, they are built specific into the SM hardware. That's because when we do, again, a thread synchronization, it's just for one thread block. We're not synchronizing the whole grid. So it just needs to run at the SM level. That's why it's much faster. So now let's think about how our histogram kernel is mapped onto the hardware. So each thread blocks run on a single SM. And the block histogram are stored in global memory. That's what we can see here at the bottom. So then each thread is issuing atomic operation into our private block histogram, which is most likely backed by the L2 cache. So that's not very efficient because we don't actually need to keep this block histogram around once the kernel is finished. So they're just temporary storage, while the L1 cache fits right there on the SM, and currently we're not using it. So if we could allocate this block histogram in the L1 cache here directly, that would be extremely efficient for us, and we would be first not wasting memory in the global memory, but also it would go faster because we would be directly reading and writing from this L1 cache. And unfortunately, we can't do that in CUDA. So CUDA provides an explicit programmable thread block local memory that we call shared memory. So shared memory is located where there is the L1 cache, and it has a similar latency and bandwidth than the L1 cache. And so the only downside of this shared memory is that it's limited. You cannot have an infinite amount of shared memory because you have a limited amount of L1 cache per SM. So if you want to allocate shared memory, you can just add the shared specifier to a variable. So in this example, we're just declaring an array of size 4, so 4 integer in shared memory. But so unfortunately, variables in shared memory can't have non-trivial constructors. It can only be the trivial type like int, float, etc. So from within a thread block, you can read and write to those arrays just like you would with any other array. And so in this example, each thread will write its own thread index into the corresponding element of the array. So thread 1 is writing 1, thread 0 is writing 0 into the location 0, thread 1 is writing 1 into location 1, etc. And so to not forget about any data race, we need to not forget to call think thread after we have done any writes to this shared memory before we want to do any reads, just like before when we were doing it in global memory. So to emphasize that this shared array is indeed shared across all thread block, you can see here, I have the first thread print out every value stored in it. So first threads will see the updates from all the other threads at this point, and so it will print the value 0, 0, 1, 2, 3, because we have used the things thread. So things thread is not only forcing the full thread we have here to be done, but it also makes the changes visible to everyone. That's why here, after we have done the 3 whites and done the sync thread, the thread 0 is able to see. And we know it's able to see because when we print the result, we correctly see 0, 1, 2, 3. That's because sync thread allow all the threads in the thread block to see all the modification made by the other thread in the same thread block. And so now that's bringing us to the next exercise. So this time you'll have to allocate the block histogram not in global memory, but in shared memory, which should hopefully improve the performance in our code. And so for this exercise, you'll have 5 minutes. Okay, time's up. So now let's take a look at the solution. So first we need to change the function signature. So we no longer need the block span histogram because now we don't use global memory anymore for it. We directly use shared memory. And so to allocate this shared memory, what we want to have is a block histogram, which will be, again, local to each thread block. And so that's why we allocate it with the size of the bin, which is here and bins. And then we want to make sure, because it's a histogram, that is initialized to 0, because then we're going to do incrementally add 1 into it, so it needs to start at 0. That's why here we're using our threads to allocate the first n bins to 0. And then we should not forget to use sync threads, because we have just either write to shared memory. So before reading from shared memory, we need to think. That's why we have the think thread. This way we're sure we don't have any data races. And then finally, we wrap this shared block histogram again into an atomic reference, just like before. And so then the rest of the code can just stay unchanged. We do the same fetch add, the same think thread, the same everything, just now instead of doing it in global memory, we're doing it in shared memory. And so by doing this, again, small changes, again, we went from 100 gigabytes all the way up to 400 gigabytes per second, so 4x speedups. So now finally, our kernel is functional and performance. Thing is, we've made a higher level mistake here. When we first started using GPUs, we relied on accelerated library. But now, because we're writing our own CUDA kernel, we're trying to implement everything from scratch all over again, while we could use libraries. So authoring a CUDA kernel doesn't mean you have to reinvent everything. Yes, maybe your specific use case is very specific, so you can't use QBlast, you can't use Thrust, you can't use Cub, and so you need a CUDA kernel, but even inside your CUDA kernel, we still have some tools for you. So CUDA offers a range of what we call cooperative libraries that speed up your kernel and shorten the development time. So for example, in addition to parallel algorithm launched from the host, like Thrust and Cub, we also have versions from the device. We have things like QBlast DX and QFFT DX to launch blast operation or Fourier transform operation directly from the device. And the same goes with Cub. But so what does cooperative mean in this case? Why do we call it cooperative libraries? So we say cooperative because we have different type of algorithm we have incarnate so far. So let's take, for example, sort. So when we talk about std sort, it's a serial algorithm. So a serial algorithm is both called and executed by a single thread. So if two different threads each call the serial algorithm, the input from one thread cannot affect the output of the other. Cooperative algorithm, on the other hand, they are invoked by multiple threads and they are executed collectively by all the threads at the same time. So you can imagine the input of this cooperative algorithm as being one large virtual array that just happened to be split across different threads. And the same goes for the output. So here in the example on the slide, a cooperative sort takes element 1, 3 from the first thread and 2, 4 from the second. And so after sorting again cooperatively, the first thread's output becomes 1, 2 because we have just sorted the array. And the for the second thread, we have 3, 4, even though this 2 value came originally from thread 1. That's why we say it's cooperative. The input and the output are shared by all the threads. So we have also used parallel algorithms, which are called by a single thread, but executed by many threads behind the scene. So from a user perspective, these algorithms appear serial, since you are not, since you just call them like any other function. However, under the hood, they're distributed across multiple threads to make the task faster. So some example of parallel algorithm we have used so far are like thread transform or device transform. But so now let's take a closer look at those cooperative algorithms. So on the slide, you can see how a cooperative reduction might work. So here, all the threads provide a single value into a cooperative reduction. So thread 1 contributes to value 0, thread 2 to value 1, etc. And so inside the cooperative algorithm, these values are written into shared memory. And after a thread block synchronization, a smaller set of threads are computing the partial sum and write them back again. And after one more synchronization, the total sum, so 6 here in our example, is written back to the first thread. So also, although this is a very basic model, this illustrates the 2 key points about cooperative algorithm. They rely on shared memory to exchange data between the threads, and they may include synchronization. Here we can see we have 2 sync threads to make the reduction work. This means that any thread in the block fails to call if any thread in the block fails to call the cooperative algorithm, the entire kernel could have a problem. We need all the threads to be included when calling this this cooperative algorithm. So now let's see how this intuition is applied into real code. So on the screen, you can see a cooperative reduction provided by CUDA. So unlike traditional function-oriented interface, CUDA exposes its cooperative algorithm as a template structure. So template parameters are used to specialize algorithm for the problem at hand. So here, for example, we can specify that we want to reduce a specific type, which is here integer, and we need to specify that our block width will be 256 threads. And so cooperative algorithm, they have a nested temporary storage type, which specifies the type and the amount of temporary storage that the cooperative algorithm will need to do the internal communication. So we allocate an instance of this type in shared memory. Then we pass a reference to that shared memory instance when we construct the cooperative algorithm. Finally, member function provide different flavor of one specific cooperative algorithm. So if we put all of that together, the usage of a cooperative algorithm looks like this. So we first instantiate the block reduction by saying we want to reduce integer, and we have a thread block size of 4. Then we allocate the temporary storage in shared memory. Next, we construct an instance of this cooperative algorithm structure. And finally, when we have this object available, we can finally call the cooperative algorithm from all the threads in the block. And so CUDA provides many general purpose algorithm at the thread block level. So you can see we have exchange, histogram, load, merge sort, redict sort, reduce, scan, shuffle, etc. And we can see here that we have what we need here. Instead of doing a block histogram ourselves and potentially producing a code that is not highly optimized, we could be using CUDA block histogram instead. So this block histogram algorithm has a few template parameters. So first we have to specify here the type of the histogram. So here in our case, it's an int. Then we need to specify the thread block size. So in our case, it's 256. Then we need to specify how many beans each thread is going to contribute to. And lastly, we have to specify how many beans we have in our histogram. So the usage of this cooperative primitive is similar to what we have just seen in the reduction case. And so that brings us to the final exercise in this section. So this time, we'll have to use CUDA block histogram in our histogram kernel instead of implementing it ourselves. And so for this exercise, you'll have 8 minutes. Okay, time's up. So let's look at the solution. So we first load the cells from the grid, just like before. This is just like before. And this time we allocate the beans locally on the stack with a C-like array instead of the subspan. That's what we are doing here. Then we instantiate the block histogram type, allocating its temporary storage in shared memory. And then we can call the histogram method to make the histogram happen. And finally, we shouldn't forget that we still need to synchronize before doing any reads or writes in memory after. So now let's recap all the things we have learned in this section. So sometimes we may want to write custom CUDA kernels because what we want to do is not covered by executable library like BLAST, UFFT, or Thrust. When we do so, we need to be careful by using ThinkThread when it makes sense to establish a barrier across threads to make sure that all the threads are done doing some modification to some data before doing another set of modification to this data. And this is to avoid what we call data races. We can use atomic to communicate between threads without producing any data races. And even when you use atomic, we still need to use ThinkThread to establish a barrier across the threads in the block. And we have also talked about shared memory. So when you need a temporary storage within a thread blocks, or when you need to exchange data between threads within a thread blocks, you can use shared memory, which is located where is the L1 cache. And so it's faster than relying on the L2 cache of the global memory. And when you're authoring a kernel, we still have libraries that can help you that are available directly on the device side. So we have CUDA that offers a cooperative algorithm that works at the block or at the WAP level, like we have seen the block histogram or the block reduce. We also have this for other more specific library, like we have QBLAST DX for linear algebra, or even QFFT DX for a Fourier transformation. And so don't ever make assumption. You should always measure performance to make sure that you are not being slowed by something or something else. Also, don't make assumption about if your code is working or not. You should use things like compute sanitizer to make sure that you're not doing any out-of-bound access. And you can also use other tools like CUDA GDB to debug your code and inside system to visualize and profile your whole application. So now let's try and review all the things we have learned today. So we have discovered what are execution space and wrote a naive cooling simulator. Then we saw how we could use fancy iterator to speed up things and avoid unnecessary materialization and do all the things in a single call. We learned about all the rich vocabulary type that can make the CUDA programming experience easier. We have also encountered serialization and learned how to avoid it by picking the right algorithm and using the right amount of threads. And we also find out about memory spaces and how when we use universal memory, the transfer of memory between host and device that will happen can take some time. And so it's better in that case to directly separate memory in order to improve performance. We have also discovered synchrony and learned how we can overlap computation and input-output operation on the CPU. We also saw how CUDA streams can control asynchrony in our program and allowing us to overlap computation and memory transfers. And we also went under the hood and discovered how the virtual memory work and how we had pageable and pin memory. And we saw how using pin memory allowed us to do host to device memory transfer faster, but also in an asynchronous manner. Finally, we have learned through this section how to write our own CUDA algorithm. So we have found out that we need atomic operation and synchronization primitives to avoid data races. And we saw how using privatization could reduce the contention when we're doing a lot of atomic in the same memory location, and to improve performance by using this privatization, but that also meant we had to do some synchronization at the correct location. We also discovered a way to store block-wide data faster by using shared memory instead of using global memory. And finally, we saw how we can use cooperative algorithm like CUB directly inside your kernel to go even faster and avoid having to implement everything from scratch. So now, if you have the time, you can do the final assessment. So in this exercise, you'll be given the code for a simulator of Maxwell equation for electromagnetism. And so your job is to port this CPU code to the GPU. And so you'll do this in 3 separate steps. So in step 1, you will port it from STT vector to explicit memory spaces using the thrust container. You should also add the correct execution space specifier and use GPU accelerated parallel algorithm. So use thrust instead of using STT transform. Then in step 2, you will use fancy iterators to avoid unnecessary materialization. So to avoid having to call, for example, transform and reduce, and also remove any temporary memory allocation that are now not necessary since we have used a fancy iterator. And finally, in step 3, you will use CUB block reduce to compute the average temperature in a thread block to coarsen the grid and save input-output traffic. And with that done, we have finished this whole class. So I hope you have learned a lot through this session, and then you're walking away with a lot of new knowledge regarding CUDA programming tools and overall how to use the GPU correctly while programming in C++ CUDA. And again, if you have any feedback, do not hesitate to fill that in the feedback section of the TLI.